Okay, welcome everyone to this continuation of quantum topology. Quantum topology. And yeah, so what is quantum about it? We still don't know. And we're going closer to why it's called quantum. Quantum. So topology, essentially the idea is we want to get rid of all topology and just want to do quantum, but I haven't explained what quantum is at all. Very, very sad. Life is very, very sad. Anyway, so let's do it. So the point is, again, we have topological objects like knots and links. Very difficult. Oh my goodness. They are very, very, very deceiving. They look simple, but they're actually super difficult. So what we want to do is we want to send them in something more familiar, like linear algebra type things. Yeah. So that's kind of the whole idea. We want to send them into linear algebra type things. And we want to, for that, we want to set up additive categories essentially, or abelian categories, or linear categories, all of that jazz, which is just a fancy way of saying we want to work in vector spaces. But sometimes we need to have some little more complicated objects that just look like vector spaces. Okay, so let's try to do this. So essentially, we have this notion of a module. Yeah. A module is, so I think as far as I understand the history, a module is nothing else than a vector space, okay? A vector space, but not necessarily over a field, but you can have, for example, over the integers or over some other ring, yeah? As soon as you have integers, you have a ring anyway. And as far as I understand, the confusion between module and vector space, which are literally really just the same, you have vectors, you can add them, you have vectors, and you can scalar multiply and add them. That's literally what you can do in a module as well. Just your scalars, as I said, are kind of more general if you want. And I think the confusion comes from, so the confusion here is that the module really should just be called a vector space and everyone would be happy. And I think the confusion comes from that the words module and vector space are roughly the same, kind of roughly originated at the same time. So roughly 1880. So module comes from modulus, was introduced as like a vector spaces over Z mod n, essentially. And vector spaces were invented at the same time as kind of linear equation type systems, right? System solving linear equations. So there was a little bit of a confusion with this name, and I make such a big point out of it because I'm probably very inconsistent and just call modules vector spaces. What can you do? What can you do? Anyway, linear category is really just nothing else than every home set is a vector space over some ground ring. Well, let's say over the integers or over your favorite field or whatever. Yeah. So it's really the idea of linear algebra in a category where now V and W could be morphisms, and you could still add them, and you could still scalar multiply them. You can subtract them. If you have a good subtraction in your ring, then that's actually pretty good. You can rescale them or whatever. Yeah. And you have one extra operation, you can compose morphisms. So you require that composition is bilinear, right? That's literally the only thing you can require, and you just require it, and it will be fine. Matrices will satisfy that. Anyway, so a linear category, nothing else than a category enriched in vector spaces, if you want. And yeah, so usually I have some ground ring or some ground field, and if it's not really important which one it is, it doesn't matter. So here it doesn't really matter, it works for anything. And it's really just the idea of doing linear algebra in vector spaces. That's literally what it is. And why do we want that? So why coefficients enter diagrams? Yeah. So we really want to take linear combinations of diagrams. That's what we want, because this is like a skein type relation that we will see all the way. That's literally the main relation of quantum topology, if you want. So overcrossing is undercrossing plus error term. This is the main relation ever, right? If you can just flop crossings over plus an error term, that's essentially your quantum invariant. So we really want to just take linear combinations of pictures, and our pictures are our morphisms. So we want to take linear combinations of morphisms. And how do we do that? We just are now in a linear category where whatever A, B, C are some constants. So for example, A equals B equals 1, C equals 0 is you can just untangle everything like DNA does it. And yeah, so skein relation picture, one picture is a linear combination of other pictures. That's what we want. We want to take linear combination of pictures. And this really makes then topology into a kind of fun calculation. So you can calculate with pictures, which is very, very entertaining. So at one point, you just need to pass time, and it's very entertaining. It's very entertaining, right? So I say it again. Literally, we just take something where we can talk about adding and scalar multiplication, and so we can add and scalar multiply pictures. And literally, we can just think of them as being like the free vector space spanned over pictures. So pictures are basis elements, and we can just add them, and we can write down equations in pictures. This is literally what we want. We want equations in pictures, linear combinations of pictures. That's literally what we want, okay? That's why we're doing it. In the end, that's why we're doing it. Right? So our pictures are morphisms. We want to take linear combinations of morphisms. So that's a linear category. An additive category is essentially the same. So you can now form direct sums. So you can take, so linear category literally says our morphisms, you can think of them as matrices. And an additive category is you have a direct sum operation. So more formally, an additive category is z-linear over the integers. You have a zero object. Yeah, why not? And you can take direct sums, and direct sums literally just mean you can put matrix blocks, like nice matrix blocks. Yeah, and the way to define it is like a direct sum is a product coproduct at the same time, so it's kind of doing both things at once. So that's literally an additive category. So linear category, additive category, kind of the same. In the end, we want to have both anyway. So we will have some coefficients over some field, and we have direct sums. So we can literally just talk about matrices. And why do we want to do that? Because it's literally like matrices without choosing coordinates. We can now think of in an additive linear category. Where's linear? Linear is here. In an additive linear category, we can think of matrices of diagrams. And we could also have linear combinations of matrices of diagrams and whatever. And we can just multiply and add them and can do all of the nice matrix compositions just with diagrams. Yeah. So literally, this that's what we will do, right? We will have some field linear additive category, and we will just usually over diagrams, and then we can really do linear algebra with diagrams, and this is literally what we want. And that's the essence of quantum topology, doing linear algebra with diagrams. Yeah, composition now becomes matrix multiplication in this case. So you can just, the way it works, it just works out perfectly. So if you want a matrix here, I will show you later, not in this video anymore, a literal calculation. So you never have to worry that things don't compose, because literally by the definition of the category, you will be able to do matrices in morphisms, and the composition will work out perfectly beautiful. And you have linear algebra in arbitrary categories, for example, in diagram categories, and that's really what we want. Oh, everyone likes diagram categories. If you don't like diagram categories, I feel very sorry. Diagram categories is a beautiful way to just pass the time. Yeah, excellent. I don't have any other good reason for diagram categories. There are probably others, but for me, it's just a tool to pass the time. And so here, this little picture will kind of summarizes what we're going to do. So linear is literally, you can take direct sums and scalar like vectors, right, of morphisms. Additive is you essentially can take direct sums. There will be something that is called abelian, which is where you can make sense of images and kernels. And all of that together is maybe what you can call categorical linear algebra. And we want to do the same in terms of identities, invisible zero objects. So for the empty diagram is a zero object, for example, or whatever. We'll see a lot of other things going on, but this is literally what it is, right? So we want to speak about things like exact sequences. We can't do that right now. We will do that when we have abelian, but like decompositions and more. So literally just representation theory, linear algebra, in which, by the way, representation theory is the same as linear algebra in categories, so categorical linear algebra. I haven't told you what abelian is, but we'll see that as we go along, right? Linear combinations, honest algebra, hey. And in reality, it's really just some form of representation theory. Anyway, I hope you enjoyed this video, and I also hope to see you next time.